Yes. Yes. Sorry. On page 116, number 6, you know what? I should have written that it is at STP, but you can make that assumption because otherwise the question's not doable. Okay, so I need to fix and put that at STP. Thank you for that. For which one? Number 5? And 7. Okay, I know 7 was a little weird. And the reason 7's a little weird is because there was a typo. This should have been on the number 4.
4 is not empirical.
Oh.
It doesn't work with C2H5, but it also has a different graph.
Okay, so we just need to fix this question. All right. So in other words, 116 is just a hot mess. Yeah? And we're not sure about the answer key here. I'll check that one as well. 5 was fine? Okay, so 6 and 7 need a little issue. Okay, thank you guys so much for correcting my errors. They won't be there for the next group that come through here, so thank you so much. All right, percent composition is a way to express how much of a particular element is found in a compound. Specifically, percent composition. We're not just looking at any old percent. We're not like percent by moles. We're not percent by volume. We're looking at percent by mass. And if you're asked for the percent composition, it literally means the percent mass of each element. So I want you to tell me what percent of the mass is oxygen, what percent of the mass is carbon, what percent of the mass is hydrogen, whatever's in the compound. Okay? So what is the percent composition of sodium bicarbonate? So you need to be able to write the formula for sodium. And do you guys know what the prefix bi means? You would think it means 2, but when we're talking about polyatomic ions, it means add an H. So carbonate is CO3, 2 minus. Bicarbonate, we add an H plus, so that becomes then HCO3, and because we have a 2 minus and a 1 plus, our charge is now negative. Okay? I mean, of course, bicarbonate is listed on your table of common ions, but it's kind of nice to know how those things work. Go. Okay, so we have Na plus and HCO3 minus, so we end up with NaHCO3. And if we want to find the percent by mass, the easiest way to do this is to find the molar mass. And if you write it out in this formula, in this format, or something similar, you will have all the information you need for the next step. So we have 1 sodium, so that gives us 23. We have 1 hydrogen, so that gives us 1. 1 carbon gives us 12. And 3 times 16 gives us 48 grams of oxygen. Yes? So now we know the grams of Na, we know the grams of H, we know the grams of carbon, and we know the grams of oxygen, and we also know the total grams. Could you use that to find the percentage of that mass, which is sodium? Yes? Is this like the easiest thing in the world? Are we liking percent composition? Yeah, okay. That's all you do is you just say, oh, I'll take 23 and divide by 84. I'll take 1 and divide by 84. And the only thing to watch out for here is if we're using our periodic table, hydrogen is just 1.0, which gives us 2 sig figs. So our percent here should have 2 sig figs, whereas the other ones will have 3 sig figs. Okay, and that's it. You should maybe at the end just check your math by adding them all up, and they should all add up to 100 or at least really close to 100. You know, do with rounding, you might end up with like 99.9. You know what I mean? But it should all add up to 100. If you're asked to find percent composition, find the percent of each element. Other times you will be asked to find only the percent of a single element. For example, what is the percent of iron, what percent of iron 3 hydroxide is oxygen? So we have Fe3 plus and OH minus. What is the formula for Fe3 plus and OH minus? FeOH3. Brackets, thank you. And I make my 3 look like a 3 and not a 2. Okay, and then you just find your molar mass of your compound. We have 1 iron, 3 oxygen, 3 hydrogen. So we have that many grams of Fe, that many grams of O, and that many grams of H. And we wanted the percent which is oxygen, so we don't have to solve for all of them. We just need to take 48 divided by 106.8, and we get it is 44.9% oxygen by mass. Okay? Last thing, do you remember what a hydrate is? Tell your partner what a hydrate is. Okay, a hydrate is what? It's compound. What kind of compound? Crystal lattice, which means that what type of compound is it? Ionic compound. And what differentiates it from other ionic compounds? It has water. Okay, where? Yeah, embedded in the crystal lattice. So do you remember I told you that you could heat this thing? And what happens if we heat it? Starts to move faster. And the water, what happens to the water? Woo, woo. Okay? And why does that happen? The IMFs break. Why do the ionic bonds not break? Because they're much stronger. Okay, excellent. All right, so you can imagine we could separate the water from the hydrate in an experiment, yes? Okay, so we could find an empirical formula for a hydrate. So let's just go back to here. There we go. And if you're asked to find the percent water in a hydrate, it's nice to just know that the molar mass of water is 18 grams. It just makes your life a little bit simpler. Okay? So let's say that we want to find the percent water in mercury 1 chloride. Now, first of all, without looking, I'd like you to figure out the formula for mercury 1 chloride. Do consult your pink sheet, please. Now, why did I ask you to consult your pink sheet? Because mercury 1 is an odd little guy, yes? It doesn't behave like normal. Normally, like if I had mercury 2 is just normal. And you would have a single Hg with a 2+ charge. Yeah? That would be mercury 2. Hg 2+. But mercury 1, how many atoms of Hg do we have? 2 of them. And this entire thing has a 2+ charge, yes? So if we were to write it out and we put the charge on each individual Hg atom, what is the charge of each Hg? 1+. Okay, so that's why it's mercury 1. Okay, mercury 1 is a polyatomic ion. It's an odd little thing. You just need to remember that mercury is strange. But hopefully, the fact that mercury is strange in its elemental form will help you remember that. What's strange about mercury in its elemental form, all by itself? It's a liquid. Most metals are not liquid at room temperature. Okay, so that might help remind you that mercury is a little bit strange. Maybe look on your pink sheet. Okay? All right. Go. So we have mercury 1, Hg 2+, and we have chloride, Cl-. What is the formula for that? Hg2, Cl2. Can we simplify that? Should we simplify it? No. Okay? And then we have pentahydrate. How do we write the formula of a hydrate? We put a dot, and then we put 5H2O. Yes, very good. Okay, 5H2O. All right, so we got mercury chloride, pentahydrate, and then you would calculate the molar mass of the whole thing. And because we are finding the percent which is water, we're going to treat water as a unit when calculating molar mass. So we find the mass of mercury. We find the mass of chlorine, and we find the mass of water, and we use the fact that the molar mass of water is 18. Okay, and then you just take your 90 grams of water and you divide by your 562.2 grams of Hg2Cl2. And don't forget, when you're showing your calculation, if you're writing it as a percent, and not as like 0.16, then you should show times 100%. Yes? Or times 100. I don't know what the mathematical proper way of doing that is, but there should be 100 in there somewhere. Now, we can apply this to some problems and make it a little bit less trivial. If you are given 16 grams of FeOH3, how many grams of oxygen can be recovered? Now, there's actually many ways to do this problem. You can use percent composition, you can use conversion factors. Why don't you guys cover up the answer and see if you can solve this problem? We have 16 grams of FeOH3. How many grams of oxygen can we get from this? And this is a case where it won't matter if you use O atoms or O2 molecules. The mass will be the same. You'll just do a different number of steps and you'll have a different molar mass in there. Okay? Doesn't matter. So give it a try. You can solve it any way you want to. Yeah. Just give me a little wave when you're done. Got 1, okay, 2, 3. How are we doing? Anyone need more time to work on that one? Okay, what could we convert if we wanted to do it by conversion, some of you probably did it by conversion. If we wanted to, what could we convert our 16 grams of FeOH3 into? Did anyone do it by conversion? Yeah? We eventually want to get to grams of, yes. Yeah, you could change it into moles of FeOH3. You could use the mole ratio. to take us to moles of O. That's an exciting O. And then from there, we could go to grams of O. That's, pardon me? Yeah, you can. Okay, so this is one way of doing it, and that would take you 3 steps. Yes? Do you want to see the work for this, anyone? Yes? Okay, I'll just do it really quick. So we have iron has a mass of what, 55.8? Yeah? Cool. 55.8. We have 3 times 16 is 48. And we have 3 times 1 is 3, which gives us 8. 11 plus 5 is 16. Carry the 1. 106.8. Is that correct? Okay, excellent. So we can say we have 16 grams, 16.0 grams of FeOH3 times 1 mole of FeOH3 per 106.8 grams. Boom, boom. And then we can use our mole ratio. We want to cancel moles of FeOH3. And we want to find moles of O. And there are 3 O's in every 1 FeOH3. So boom, boom. And then finally, we want to go to grams of oxygen. So we want to cancel moles of oxygen, find grams of oxygen. 1 mole of oxygen has a mass of 16 grams. And so that will give us some number or other, which I assume you guys have all solved for. What did you get? Okay, it's going to be easier for me to solve than to hear you guys. That's sad, right? Old ears. Okay, 7.19. Did I do it wrong? No, I did it right. Okay, 7.19 grams oxygen. Okay, so that's one way we could do it. Perfectly valid? All good. Is there another way we could do it? How else have people done it? Yeah.
Like use the percentage of O.
You can use the percentage of O. So let's find our percentage of O. We have 48.0 divided by 106.8. And I'm actually going to leave it in its decimal form because I'm going to use that to multiply anyway. So 48, and I'm going to put grams of O over grams of FeOH3, so I know what I'm talking about. Because otherwise, if I don't put those there, I've just got random numbers floating about, and it probably, like, whoever's looking at it later won't know what I'm talking about. Yeah? So we have 48 divided by 106.8 equals 0.44944. There we go. And if we want to know the grams of O, that's going to be our percent O times molar mass, times 16% of O times mass of FeOH3, which is going to be 0.44. So many fours. 4494 times, what was it, 16? 16 equals, guess what? 7.19 grams of O. Yay. There's a third way. Did anyone do it a third way? Yeah? Like this? Yeah. So what we have here is we have a gram ratio, yes, which is not something we use a lot, but it is true that for every 106.8 grams of FeOH3, we have 48 grams of oxygen. So if we want to go from grams of Fe, yeah, you just keep it in fraction rather than putting it as a decimal, yeah? And you don't have to convert to moles in the middle. So this is actually the shortest way of doing it. But any of these are perfectly good. Yes? So your choice, which method you use. And if you do this, you will get 7.19 grams of O. So do the one that makes sense to you, that you feel most comfortable with, that you're not going to forget or get confused by. Yeah? So are we good with that? Okay, excellent. That was percent composition, and I think that's it for that. Yeah, so we have method 1, find the percentage. Method 2, use the mass ratio, and I didn't have the other one where you went through moles, but you can definitely do that too. All right, moving right along. 5.7e on page 121. Basically, what we're doing here is we are putting together what we learned in finding percent. We're taking percent composition, we're taking empirical formula, and we're taking molecular formula, and we're putting them all together. Okay? Before we look at this, tell your partner the little poem. And if the poem doesn't help you, if you're like, I cannot remember the poem, you can think, what is an empirical formula? It is the ratio of atoms. And how do we count atoms? We count them in moles, okay? So the empirical formula is the ratio of atoms. We count atoms in moles. What is a measurable quantity that we can use to convert into moles? Well, that's grams. Yes, we can find moles from mass. And if we want to find the ratio, we find ratios by dividing. And then that number has to be, make it a whole number because it's a whole number ratio. Okay, so what's going to happen is we will be given the percent composition of a compound, like what we were just finding, instead of being given masses. Last day I told you the mass of copper is 3.2 grams. Today I'm not going to give you the mass of copper in the compound. Today I'm going to say we have a compound here, which is 48.38% carbon. It is 8.12% hydrogen. And it is 43.50% oxygen. Now remember, we still need to have a mass. We're going to have to make an assumption here. What would an easy way to get mass ratios here be? You could times it by the molar. Well, we don't have a molar mass. We can multiply by the total mass. Now, we're not given a total mass. What would be a really easy total mass to work with? 100, because if I have 100 grams of the compound, how much of that compound would be carbon? 48.38. If I have 100 grams of the compound, how much would be hydrogen? 8.12 grams. Is this making sense? You could choose any value you wanted. You could say, oh, I'm going to assume that I have 3.86 grams of the compound. And you could say 0.4838 times 3.86 grams. And you could go and do that calculation. But that seems like a lot of work, right? And you'd have to do it for all three of them. Whereas if you assume you have 100 grams and not something weird like 3.86 grams, you don't have to do any math. It just gives the percentages are the masses. Yes? So we have to assume we have 100 grams of the compound. And you need to write this down. You must write this down. It's worth a half a mark. Okay? Assume you have 100 grams of the compound. Yep. Now, this next step, you don't actually need to show this bit here, where you actually say, okay, my grams of carbon is 0.4838 times 100 grams equals 48.38 grams. You can just rewrite the percentages as grams. Okay, so you don't have to show this. You do not need to show this calculation up here. So, here's our question. We assume we have 100 grams of the compound, and we're going to start with our masses, which are just 48 point blah, 8 point blah, and 43 point blah. Yes?
Because the 48 and 48 always going to add up to 100.
Yes. So the reason it works is because we have assumed that we have 100 grams. So you are telling the person, you're assuming that whoever's looking at your work doesn't know what you're thinking. And so you're telling them, if I have 100 grams, then I have 48.38 grams of carbon, right? And you're not assuming, oh, I have 50 grams, in which case I would have 24.19 grams. Yeah? So it's just a kind thing to do. Anytime you make an assumption, it is kind to your reader to say what that assumption is. Okay? Yes?
You have to write down the assume that.
Yes, you must write the assumption. Okay? Okay, I'm a little overexcited there. All right? It's a free half a mark. Just write it down. Okay? So we have written our assumption. Assume you have 100 grams of the compound. And now we can just throw down our percentages as masses. Here is my grams of carbon, my grams of hydrogen, and my grams of oxygen. We've just rewritten the percentages as grams. Find the mass. So we found the mass. Hooray. What comes after find the mass? Mass to moles, because we need the ratio of atoms. And how do we count atoms? We count atoms in moles. So find the mass to moles, we use our molar masses. Okay, so now we have moles, moles, moles. And then we do a division. Who do we divide by? The smallest one. This is our smallest one. Okay, and you'll notice how many digits am I keeping? Usually. The only reason this one's not to 4 digits is because it only gives me 3. Okay. Keep 4 digits. Why? It'll give you nice numbers that are like 2.99, yes? Or 1.328, which is really close to 1.33. It won't give you numbers like 1.15. And you're like, what the heck is 1/5 a fraction, 15 a hundredths? And then you're like, no. They're going to be either 1/2 or a quarter or a third or a half, a third, a fourth, 2/3, 3/4. Okay? So if you keep enough digits, you won't end up with weird numbers that don't look like they're actual fractions. Okay? So keep 4 digits. And then either on a separate line, or you can show the process up here. You can say, I am dividing by the smallest, which is 2.97. And when I do that, you'll notice there's no equal sign here, right? Because 4 does not equal 1.48, right? 4 does not equal 1.18. So we do not want to have an equal sign there. You could show an arrow if you wanted to. Be like, ah. Or you could be like divided by 2.719. And if you put an arrow there, then it's not really like equal. You haven't said equals. Anyway, we get 1.48 and we get 2.98. And those are really close to 1.5 and 3. So we have 1.53 and 1. And we multiply by 2 to get our whole numbers. We get 3, 6, and 2. So it's C3H6O2 is good. Okay. Okay. And now we're just adding on a step. Do we need to stand up and like take a little mental stretch break? Let's take a little mental stretch break. Everybody stand up. Okay. And because you're my prisoners, my students, you get to do the stretches that I need to do in my life, okay? Because, I'm getting old, and I have yes, you may go to the washroom. I have this terrible, little neck hump, and it's driving me crazy. I feel like an old lady. So I want to get rid of it, and it's good for your posture, too. And we all spend our time, all like this over our phones. So you, too, may someday get a neck hump, and you'll be like, oh, my God, what do I do if I get this horrible, thing in the back of my neck? So what you do is you tuck your chin in and you pull it back, okay? So you will not, I look terrible. I look like a frog, okay? But what you do is you put your hands over your head, you tuck your chin back, and then you pull your hands back and you pull your shoulder blades together and you hold that for 30 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We're going to do only 20 because we don't have time for this. Okay, and then we're going to move to a Y. Okay, and put your shoulders down and pull your shoulder blades back together and tuck your chin in. And then we count to 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And because we don't have time, we're now going to move to our next one. So it first goes I and then Y. I, W, and then it's either a Y or a W. Which one do you want to call it? Y? Okay, so I, Y, T. And again, it's supposed to be 30 seconds, but we'll do 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And now we do an L. Your little arms make little L's. Okay? Maybe this is the W. I don't know. Anyway, like this. And then 15. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And if you do that once a day, you will hopefully never have the neck hump problems that I'm having. So you can just go home and do that in the evening once before you go to bed or whatever, when you wake up in the morning. If you ever get old and I'm still alive, you can probably find me on Facebook if it's still around, and you can be like, what are all the things I need to do to stay healthy? Because I've learned them all, because my body is now falling apart. It sucks. I like getting old. Being 50, over 50, I love it, but I don't like what it does to the body. Yeah? Okay. So here we have our percentages. Percent carbon, percent hydrogen, percent oxygen. We are told that the molar mass of the compound is 140 grams per mole. When it says the molar mass of the compound, what does that mean? Tell your partner. It is the molar mass of the what? The molecular formula. And now we're asked, what is the molecular formula of the compound? So all we're doing is we're taking all the steps that we've done up till this point, so I'm not going to spend a lot of time doing each of them. The first thing we have to do, because we're given percentage, is what is it? We have to assume you have 100 grams of the compound. Write this. And then you have to say, okay, all of my percentages have now become, they're no longer percentages, now they are grams. Okay, so they were percentages and now they are grams. What do I do with the grams? Use the molar mass to convert to moles. Okay, so we found the mass, percentages became mass. We take our mass and we convert it into moles. And now that we have moles, what do we do with all those moles? We divide by the smallest. Here's our smallest. Okay, so we take 5.7192 and we divide by 1.427 and we take 8.63 and we divide by, you don't have to write this each time, that's why I like writing it at the top, it just assumes I do it all the way across. 1.427 and we take this and we divide by 1.427. And if you haven't noticed yet, one of these things is always going to equal 1 because the smallest divided by the smallest will always be 1, okay? And we get a 4, we get a 6.05, which is close enough to 6, okay? Because we're not going to have like, what would that be? That would be like a 20th. We're not going to multiply by 20, okay? 20 is too many. And then we have a 1. And we don't need to multiply till whole, so we have 4, 6, and a 1. And we get our empirical formula, C4H6O, and we say, good Lord, that was a lot of work. I hope I'm done now. Was the question asking me for the empirical formula, or was it asking me for something else? It was asking me for something else. It was asking me for the molecular formula. How do we find a molecular formula if we know the empirical formula and the molar mass of the molecular formula? Tell your partner. Oh, yeah. We have to do a conversion or a division. We have to do a division. What are we dividing? Yeah, molar mass of molecular formula divided by the molar mass of the empirical formula. This one was given in the question. Yes? And the molar mass of the empirical formula you find from the periodic table. So, molar mass of the empirical formula, 4 carbons, 6 hydrogens, 1 oxygen equals 70. Molar mass of the molecular formula was given in the question. 140 divided by 70. Oh, thank goodness. It is a whole number. What would I do if it wasn't a whole number or something really close to a whole number? If it wasn't close to a whole number, I'd say, oh dear, I've done something wrong. Or possibly Ms. Spence has done something wrong, which is always the other possibility. Yes? I'll try and make sure that when I write your test that we don't have any boo-boos like that, okay? Yeah. But if you are writing a test and you are like, because you've seen, I make mistakes all the time. I make typos. Don't get stuck on a question and be like, why is it not working? Don't assume that I have done it right. Just be like, ask the question. And if I'm absolutely 100% sure that I've written the question correctly, I will let you know. But don't sit there and be frustrated that you cannot find the answer because maybe the answer isn't, if it's a multiple choice, maybe the answer isn't there. Maybe I typed it wrong, right? So do ask if you think I've done something wrong, okay? All right, anyway, we found the number 2, so we take our empirical formula and we multiply by 2. Is good? Okay. And then there's some exercises here. Do you want to kick out combustion analysis while we're at it today? Okay, and this will finish the unit for us. Oh, no, we need to do our lab, our demo lab. But it's going to take only like a minute, so that's okay. Did you have a question? No, okay. Demo lab, meet me over at the fume hood, okay?
Where did I wrote it? Oh my God.
Do anything. I'm going to pass this around so you can make some observations, okay? And your class is the one that says United, okay? The other block says 30 milliliters, but you can look at either of them, okay? So I'll pass one this way and I'll pass one this way. That way you'll all get a chance to see and make some observations about it. What happened? The experiment.
Wait, it's originally white, right?
Steel wool, like iron color.
Yeah, but that's so much different. It's like
It looks different, doesn't it? Yeah. No. Some of it's eraser? Yeah. Some of it will do. Anyone not get a chance to see one of them? Yeah. Over there, you haven't gotten it? Okay, who's got the other one? You guys still working on that? Okay. Here we go. There you go.
Ryan.
That's what's in the input. It stops moving.
You totally do.
Did you?
Oh my god, no, I forgot.
It's not gonna kill you.
What does it smell like? There's like, I can't smell it.
Well, it's ammonium
Smells
chloride.
like-
What do you think it probably smells like?
Smells like.
Ammonium chloride smells like. Smells like ammonium chloride, but it smells like probably smells like ammonia.
I don't know what that smells like either.
You don't know what that smells like?
Nope.
Ammonia is a cleaning product.
Oh.
It's found in a lot of like window cleaners and stuff like that. So like Windex has ammonia in it. Yes, I was gonna say, pee has ammonia in it. So it might smell like pee. Yes. Okay. Okay, anyone else not get a chance to see it? We're all good? All right. Did you get to see it? Yeah, okay, good. All right, so what I'm gonna do now is, oh, you can see the part where I had my little clippers on it, right? And it didn't do anything. Where I had the, what do you call them? Slow commas. So,
Like, was it like that yesterday? Like, did it gradually?
it's a gradual change, okay? In fact, I should let you observe some steel wool that hasn't been, had anything done to it. I forgot to say that. So this is a pipette. Okay, a pipette. It's actually a Pasteur pipette. What's the liquid? It's the ammonium chloride. Okay, you could use a medicine dropper, but medicine droppers are like over there, and there were a lot of you in the way, so I grabbed a Pasteur pipette. Pasteur pipette. ASTR. Two squares. Well, I'm going to show you the old steel wool. Okay, while we're here, I'm just gonna pass around some steel wool. You can make observations on this. This is what it would have looked like yesterday. Okay? Anyone else? Go. Over here. Go. Over here. Go. So you can make some observations of the untreated steel wool. Once you're done, make sure everyone else around has had a chance to see it, and then you can put it back in this little bag here. Anyone not have a chance to see?
Smells like it smells like
You guys none of those ones?
No, it was also.
Yeah. Anyone need to see it? We're good? Okay. And we're done for today, so you can go back to your desks. Yes. Oh, that's okay. Yeah. So you can do what you're gonna Yeah, yeah. And I think it's looks like it's written by I know that it would look better in the dark. Yes. Yeah. And so reading it, because honest to God, the very first, so I don't just use. Okay, now while we're here, I would like you to think about what the steel will look like before and what it looked like today. And maybe try and think to yourself, what happened? Maybe just have a little chat about that.
What is the formula?
What is the what? Yeah, we've had a question, and the question was, what is the steel wool made of? You can chat about that, and then I'll get with you in just a second. Yes, and yes. Oh. So what is steel made of? What is steel mostly made of? It is mostly what element? Iron. Okay. And what did you notice happened to it between yesterday and today? What changes did you see between the one I showed you that was like the original and the other one? Yes?
It turned a bit red and silvery.
Turned red. And silvery. Now, I'm going to tell you right now, probably the little silvery looked like a patch like this. Did it? Yeah. And that was because when I had the crucible tongs, the crucible tongs prevented the iron from coming in contact with the solution. Yeah? Yes. Did it oxidize? Have you guys heard that word before? Yeah? So what would it mean if it oxidized? What would that mean? It reacts with oxygen, yes. Okay, so we are partway through the reaction of iron with oxygen. Yes? Okay, and we still have to wait until tomorrow. I tried to make sure I got some of the ammonium chloride onto the steel wool. Yes? Oh, where did the oxygen come from? The air. Okay. And if the iron is reacting with the oxygen, here is something for you to think about. What was the purpose of the ammonium chloride? Because I've had that steel wool in that plastic bag, you know, the ones I showed you that weren't reacted. I've had that in that plastic bag for years, and they still look the same. If I don't put the ammonium chloride on, nothing happens. Okay, so you're going to think about that. You don't have to come up with an idea today, all right? Because we aren't going to finish the lab until tomorrow, but you can ponder it, have a nice conversation with your parents over dinner about it, maybe, right? If it were my son and he brought that home at dinner, I'd be like, oh, what an exciting topic of conversation. Thank you for bringing that home to me. I'd be so excited. It would be kind of pathetic. But anyway, for homework, now, if you didn't do yesterday's homework because I did not successfully post it, you can do some of that, okay, enough to feel good about it. And you can try, now percent composition, number 1 for sure, because it just kind of gets you thinking about what it is. So that's on page 119. I mean, I don't know how much of this you need to do. Here's a hydrate. Do the hydrate one. Do number 5, 4, 5. Ooh. 4, 5, and 8. 1, 4, 5, and 8. Actually, let's make it 1, 2, 4, 5, 8, just for fun. Page 119, and then
Wait, 1, 2, 4, 5, 8, 1, 9.
from 119, $122, number 1, and $123, number 3.
She got it. What?
And if you feel like working ahead, you can do some of 122 to 125. Oh, I did 1 and 3 already. Never mind. I don't know what I'm talking about. Never mind. It's all good.
It's not I would get like
I'm adding 125, number 6. There we go. There you go. Or you can just do whatever smattering of questions from that area that you want to. Okay?
Why do you have a dog on this dog? More money. What you should.